Hi, everyone. Welcome to workshop number 2 of the WiDS Global Datathon workshop series. My name is Keiko Kamei. I am a lead scientist at FICO and a WiDS ambassador in the San Francisco Bay Area, and I will be your host today. I'm thrilled to be joined by our presenters, Kylie, Caterina, and Liana, who are all students at University of San Francisco and who have really thoughtfully designed and put together this series of introductory tutorial notebooks that serve as a great starting point for the global challenge. Some housekeeping items before I turn it over to our presenters. Please keep yourself muted while our presenters are speaking so to minimize disruptions. If you have any questions during the workshop, please put them in the chat. Valerie and I will be monitoring the chat, and we will have time for Q&A at the end of the session today. Lastly, this workshop is being recorded, and it will be made available to you on YouTube and on our resource platform, so you can access it again after today. Okay, and with that, I'm going to turn it over to our presenters who will be covering the topics of data pre-processing and preparation steps. Over to you.
Hello, I'm Kylie Cancilla. I am a third-year data science major at the University of San Francisco, and I'm excited to be helping with their Global Datathon 2025 challenge and providing these workshops and resources for all of you participants.
Hi everyone, my name is Caterina. I'm a second-year data science student at the University of San Francisco, and I'm really excited to be helping out with this datathon.
Hi everyone, my name is Leah. I'm a second-year student, data science student here at University of San Francisco. I'm also excited to be working with you all. And with that, I think we're done with our introductions and we can go ahead and jump straight into our workshop for today. So for our WIDS Women in Data Science long-term vision, we envision a future in which women are fully integrated and represented in all areas of data science and share equally in decision-making, economic prosperity, and opportunities. For our workshop today, our goals are exploratory data analysis, encoding categorical variables, merging metadata, and functional connectivity matrix, and also missing values. So for the first part, which is our exploratory data analysis or our EDA, we will be talking about how to process our data and reviewing its parts. And we will also be visualizing different correlations and making the possible inferences by figuring out relationships between different variables that we will be working with. And then the rest, such as encoding, merging, and also dealing with missing values. These next parts work on these data frames directly in order to prepare it for machine learning. And then for the mission of Women in Data Science is to change the field of data science across the globe by elevating, educating, and empowering women to achieve 30% representation of women in data science by 2030. And then just to give a brief overview of what we'll do in the Datathon itself, the challenge of the Datathon. This Datathon challenge aims to answer this question: what brain activity patterns are associated with ADHD? Are they different between males and females? And if so, how? Also, to work towards the answer to this question, participants will be asked to build a multi-outcome model to predict both an individual sex and their ADHD diagnosis using functional brain imaging data of adolescents and their socio-demographic, emotions, and parenting information. A multi-outcome model is designed to predict multiple target variables simultaneously using a single machine learning model. So these are the outcomes which are expected. 1 is for female, 0 is for male, 1 is for individuals with ADHD, and 0 is individuals with no ADHD. So most of the brief overview about the Datathon challenge itself, we talked about it in the first workshop, and you can refer back to that if there are some details that we won't be going over this specific workshop today. Okay. To start, of course, we need to load our data sets and to prepare the program or medium in which we will work with our code on. So now we're going to do a quick overview of loading a Jupyter notebook. So for this Datathon, you may be working within a group, of course, and it is recommended that you use Jupyter Notebook as the medium for programming. You may use different tools and also different languages according to your preference, but for this workshop itself, we will be focusing on tools such as Python and Jupyter Notebook. So step one is to download Python, of course, and through Anaconda, which is an open source distribution platform, which we can use for this Datathon. It's recommended as it does help you work in groups and share work efficiently with your teammates. And it also contains some standard packages, which we will be using heavily in this project. You will also see it in the code that we will be presenting to you today. And then step two, we can set up by creating a virtual environment. So you open your terminal, and then these are the following instructions or the code that you have to input in your terminal or your Anaconda prompt if you're on Windows. And then for the step three, we can move on. Yeah, for the step three, creating your notebook, this is just by opening your terminal, navigating to your desired directory, activating your virtual environment using the code that you just saw in the last slide, and running a very simple command. And then this will activate Jupyter Notebook and open the program itself on your device. So I know that was a very fast overview of how to install Jupyter Notebook, but I think it's recommended that you navigate this on your own since we have different devices and different ways of dealing with this. So more resources are available at the Community Hub under the Technical Resources section about how to install Jupyter Notebook, and also how to navigate it and what you can do to just explore the program itself. So yeah. Okay, now we'll be talking more about loading in the data frames. So as you can see here, first, we will be loading in the categorical data frame. All right, so yeah, so this is the categorical data frame. And as you can see, these are the column titles and also, sorry, the variables within the categorical data frame. So the outcome or what each integer represents specifically in the categorical data frame, this ranges from like demographics, where the MRI was done or what location it was done in or performed in. Yeah, demographics and also details about parent education, the level of education and such. And so again, the outcome of what each integer represents can be seen in the data dictionary in Kaggle, which we also talked about in the last workshop. And then next is the functional connect home matrices. So I know that as you can see, when it's loaded in, it can be overwhelming to see it individually in columns or in rows. Kylie will actually be talking about how this is integrated into our data sets with both, or merged into our data sets with quantitative and qualitative variables. So just again, just a brief overview what FCM is. Functional connectivity matrices refer to how different brain regions interact as measured by the correlation between activity in paired regions. Yes, and then moving on to loading in our quantitative variable train data frame. So this is our quantitative data frame again. So these are our variables. So these contain mostly our variables from different instruments measuring a social status, also different behavioral questionnaires and such. So again, most of these or all of the information regarding these variables will be located in our data dictionary in our Kaggle. Yes, and then lastly, I just wanted to talk more about this is the solutions data sets which contain our target variables. Again, Kylie will also go further in depth regarding how we use this data sets and merge it with our feature variables, which are our quantitative, qualitative, and of course, we just talked about our FCM data frames or functional connectivity matrices data frame. So in order to train our model, we need two things. We need an X-train data frame containing these variables, quantitative, qualitative, and our FCM. And then our Y-train data frame containing our target variables, which we see here. So again, what we're working towards is our outcomes for both sex and the presence of ADHD within our participants. So that's our training, our target variables. Yes. And then I just wanted to emphasize again our participant ID. So as you can see in all of the data frames that we just loaded in now, we have participant IDs, of course, and this is a very important as it is a unique identifier for each participant. And this is key to merging our data sets and of course, ensuring that the process is organized and accurate. So again, how we use our participant IDs, how we merge these different data frames, Kylie and Caterina will be going furthermore into these topics further on in this workshop.
So we're gonna switch back to the presentation, and I'm gonna introduce real quickly what is exploratory data analysis, which we're gonna go over now real quickly, which is a really important part of data analysis and machine learning in general, because it's a step that is fundamental before performing the machine learning itself. So exploratory data analysis is the process of examining and summarizing a data set to understand its structure, detect patterns, and identify any issues like missing data or outliers. It's a crucial first step, as I said before, in any data project to prepare for analysis and modeling. Especially in our case, we're preparing for modeling and to fit a machine learning model later on to predict ADHD and gender. So why is so important? So for 3 reasons. First of all, to understand your data set. So you want to understand the data distribution. ADA really reveals the distribution of variables, for example, like ADHD and gender prevalence, and also reveals if there's any imbalanced outcomes, if there's like any if the data set is a gender, there's a gender domination in the data set. So if there's more more subjects of one gender rather than another, and also just a feature overview. ADA helps us with identify categorical and numerical variables and their role in the model. For example, like this is just an example, but parent education level, which is categorical, might affect ADHD prediction in some way that we didn't think about before, and then can kind of help enrich our machine learning model later on. A second reason why ADA is so important is also to detect issues. So first of all, one issue is missing data. ADA identifies missing values and handles them because no data set is perfect. So there's going to be any values in the data set. And we will go over later on, Leah will go over later on how to handle NA's values at the end of the workshop. And then another issue that might arise is outliers, data point that differ significantly from another observations. They're like kind of the standard observation of the variable itself, and that can easily influence your prediction and the output of the machine learning model and the performance of the machine learning model, which is finally what you guys are going to be evaluated on. Third reason why it's really important, ADA is really important, is also to discover relationship and trends. ADA helps determine how predictors relate to outcomes, which inform feature selection. Plots might show that hyperactivity, for example, this is just an example, but by looking at plots of visualization, you can discover that maybe hyperactivity scores are strongly associated with ADHD, while, for example, parenting style has less impact. This is just an example just to explain why ADA is so important. So key tools of ADAs are descriptive statistics, mean, median, and count, and many more that I'm going to go over later. And then data visualization also is really important. So bar plot, histogram, scatter plot, and box plot. And we're going to see some of those right now. So we're going to switch over to the notebook. So we're going to just practice some of the skills that I talked about before, or just see it in action kind of thing. So this is just a definition again of exploratory data analysis. We can go over it. We can just skip over it, and then so there are 2 functions that I highlighted here because I think they're really important when doing exploratory data analysis. So .info and .describe, they both summarize each data set, and I think they're really important because by summarizing this data set, you can see all the columns. You can see that we have for the train 1,213 entries, and also you can look at the type of the column and how many non-null count we have. So how many non-NAs values we have. And So another really important function is dot value counts to understand the distribution of the categorical values and how each categorical values, how their subjects are distributed between the different variables. So for example, this is it's the parent to occupation, this variable that I chose right here, and a dot value counts. And so we can kind of see what what is the category that it's most popular, I guess, in this column. And you can definitely see that the zero variable, I don't remember on top of my mind, so we can go look in the data dictionary what that looks like. A zero is homemaker or stay-at-home parent. So apparently this is really important to know, just like the parent to education that is most popular is between our subjects is stay-at-home. So that's something to keep in mind. Another thing you can do, of course, during during exploratory data analysis is visualize distributions. So in this case, I visualize the same distribution. It's the same data as before, but in this case, I plot it as an histogram, and in the y-axis we just have the count. So you can see that again, the zero category is the one that it's most frequent. Also, we want to understand this is the distribution of categorical values. This was a categorical values, but we kind of want to also be able to visualize distribution of quantitative variables. In this case, I just chose one quantitative variable. You can choose whatever you want, but I was curious about this one. This is MRI track age scan, which is the scan age by the MRI of the subjects. And you can see that oh my god, this graph is really big, but the most popular, let's say age, it's around 8 or 9 years old, which is kind of telling us that our data sets is mostly of young subjects. So that's really important to notice. Another thing that I think is important is to analyze distributions, as I said before. So we can look at distribution for ADHD and gender. Since ADHD and gender are your targets, you want to really know what are the distribution of both of them. So first of all, I looked at the ADHD outcome, and we can see that almost doubled of the subjects are diagnosed with ADHD, while only 382 are not diagnosed with the ADHD, which makes sense because the whole data set is about predicting ADHD. But you kind of also want to take notice of this class imbalance. And then we can also go look at the gender distribution. The variable is whether the sex is feminine. So you can see that for under 16 are women, and just 797 are male. So this is actually pretty important because gender imbalance in the dataset might introduce to like biasing modeling, and do you want to address this during data preparation? We actually don't go over how to address this in this workshop, but you can definitely look up online. There's a lot of ways. We were just trying to cover as much as possible, and we didn't get to this. This is just a graph to, again, see and visualize what a gender distribution is. Okay, now we can go back to the presentation. Okay, so I'm gonna go over more what those case statistics and exploratory data analysis are, and also some important concept in data exploratory data analysis that it's important for us to cover. So first of all, mean and median. They just measure the central tendency to understand typical values. I'm sure you guys all are familiar with those two names. And then we have standard deviation and variance. They assess data spread and variability. Also, skewness indicates data symmetries, whether our data set is more to the left, to the right tail dominance, or whether our data points are more towards the left or the right. And then we have missing values, so analyze gaps in the data to ensure accurate modeling. All those things are really important, and we don't cover all those in these data sets, but those are part of ADA, so feel free to research more on those. And then we're gonna talk more about also resources you can use on to get a better understanding of what those statistics are, and to just explore more. A really important concept is correlation, because it shows up really a lot of time in our in this global challenge. So correlation as a definition of correlation is correlations measures the strength and direction of the relationship between two variables. Application of correlation is a high correlation might indicate that one variable is usable in predicting another one. The range is from -1, perfect negative, to +1, perfect positive. What high correlation means, so high correlation, so values closer to like +1 and -1 indicate a strong relation between the variables. And I'll give you guys an example in the next slide. But positive correlation is a perfect positive correlation. As one variable increases, the other one also increases consistently in a linear manner. -1 instead is a perfect negative correlation. As one variable increases, the other one decreases in a consistent linear manner. And also, so low correlation is that when values are really close to 0, and that suggests a really weak or no linear relationship between the variables. This means changes in one variables are not really associated with changes in the other. So why it's helpful? It helps us to identify predictive variables and uncover relationship. Another reason why correlation is so important in this Datathon is because we find correlation in function connectivity matrices. So fMRI is, as I said in the last workshop, but just to like reiterate over it, measures brain activity. So basically, resting state fMRI measure brain activity using blood oxygen level dependent called also blood contrast. How it works is that active brain regions consume more oxygen. Blood flow increases in this region. fMRI detects those changes in oxygen level and infers neuroactivity. So why is this important? This is important because in brain research, correlation can be used to identify how different brain regions interact during the rest or task. And we find this in the function connectivities because the function connectivity matrices describe interaction between different brain regions, right? So when we measure activity using fMRI, we check how strongly 2 or more regions cooperate or communicate with each other. This can help us understand brain function and patterns, including those associated with ADHD, which is our final goal, right? So just how like we measure the correlation between two variables, we can also measure the correlation between two brain regions and their activity. Actually, it's the measure of the correlation between the activity levels of the different brain regions. So if you want to just remember, like functional connectivity matrices are a matrix where like rows and columns represent brain regions, and we have on rows and columns the same brain regions, and each cell shows the correlation between activity in brain regions. So this relationship is captured through the relationship between the different brain regions captured by the connectivity matrices. In ADHD research, the functional connectivity matrix can help to understand abnormal brain patterns. So by examining how different brain regions correlate with each other, research can identify a typical brain activity associated with ADHD. That's why the functional connectivity matrix is really important in this challenge, and that's why it was added in predicting the multi-outcome model. For example, like just to give an example, like certain brain regions might have lower or higher correlativity than in atypical brains, which can provide insight into the neural basis of ADHD symptoms. So just as correlation reveals a relationship between variables in general, functional connectivity matrices also help us understand the relationship between brain regions activity. And also these matrices, by using fMRI data, allows us to examine how specific brain regions are interacting and how this interaction might differ in conditions like ADHD. So that's the point of adding the functional connectivity matrices to this challenge. So just to go over some examples from the dataset itself, this is the test dataset on the bottom of the slide, and that's the functional connectivity matrices. So highlighting in green, I just highlighted some of the strongest correlation that I noticed. I personally think that it's really strong to have a correlation of like 0.77, as for example, between this 0 brain regions and the second brain region. And then between the 0 and the 5th row, I think those are like pretty strong correlations. Instead, in the yellow, I highlighted kind of like correlations that sit between like 0.5, 0.4. And then I left kind of like blank or in white, just really correlation that are really close to 0, so are probably gonna be really weak, like the one negative 0.08 between this the 0th row and the 3rd column. That's a really weak correlation. So yeah, I hope that was kind of like clear. Or you guys feel free to ask question at the end of the workshop. Let me go to the next slide. So what it means for a variable to be predictive. So I think that's really important in since we're gonna try to fit a multi-outcome model, we want to understand what it means for a variable to be predictive. So a variable is predictive if its values are associated with the target variable. For example, in this case, of course, ADHD and gender. That's what we're interested in mainly. So for quantitative data to test predictiveness, you can use histograms or box plots to visualize distribution of quantitative data. I personally like suggest first like looking in a visualization, because I think once you see it, you can really notice correlations or relationships that you didn't see before. For example, an example is just you can visualize the distribution of color vision test score. Also, you can use scatter plots to like see trends between two different quantitative variables. For example, hyperactive skills or like positive parenting skills. You can like put them in a scatter plot and like look for correlations between two variables, and then can help you kind of like, if they're strongly correlated, they might overlap, and so they might overlap in the information they provide to the model. So that's really important to notice. For categorical data, you can use bar plots to compare groups. You can use, for example, ADHD rates by parent one occupation. That's something I think we're gonna go over next on the notebook. So key question to keep in mind when going over ADA, I think just as a general overview, key questions are which variables are most predictive of ADHD and gender. You want to know those because those are going to make your model, your machine learning model, way stronger when you're building it. And then their strong correlation worth exploring further? So you want to find this correlation and what insights can be drawn for modeling. Okay, so now we're going to switch over the notebook again, just to kind of like put in practice what we just talked about. So for quantitative data here, I just printed columns, and I just chose a column. I was really interested in the emotional problem skills, so I went on to explore that. And what I did is that I basically I plotted the distribution of the emotional problem scales, and the goal here is to explore whether there are difference. Whether there are difference in emotional scale problems scores between individuals with and without ADHD diagnosis. The box plot visualize kind of like before the box, sorry, this just I'm gonna go over the box plot later, but this just visualizes kind of like what is the distribution before actually going to whether someone has ADHD or not. You want to know what is the distribution, and the y-axis is just the frequency. So how many people are in the kind of more 0, so there's a lot of people that are more into the 0 to 2 kind of like emotional problem scale score. So that's important to notice. And then to really examine the relationship between emotional problem and ADHD outcome, as anticipated before, we're gonna look at a box plot. So this is just the code of the box plot. Please feel free to like go back at it and like look at it more, especially if you're not familiar with like tools like Matplotlib. There's a lot of resources online that we can point you to at. But for now, this is the box plot. And the box plot basically it just examines the relationship between emotional problems and ADHD outcome. So the goal is to explore whether there are like difference in the emotional problem scores between individuals with ADHD diagnosis. And the box plot visualizes central tendencies. So median in this case, the line that you see in the middle of the box plot in the blue box is the median, and the variabilities or interquartile range, and emotional problems. And we want to gain a deeper insight into how emotional problem skills interacts with ADHD outcome. This step is critical for building a robust model that reflects real-world data relationship effectively. So we want to really know whether emotional problems is giving us some new insights in whether someone has ADHD or is going to have ADHD or not. So some observation from this kind of graph that came to mind to me, but there's probably many. The box plot reveals that individuals diagnosed with ADHD tend to have a higher mean score on the emotional problem scale. As you can see, the mean score of the one category, which means higher, which means yes, ADHD diagnosed, have a higher median score. Sorry, the box plot measures the median. The box plot for the ADHD group displays greater variability. As you can see, like the variability of the box plot goes from 0 to all the way up to almost 8, and also we can see a lot of outliers. Those points are really outliers. And then this suggests that emotional problems are not only more pronounced, but also more diverse within the ADHD group. So that's something to notice. Now we're gonna go over the categorical data itself. So I printed the column and I just chose the column I was most interested in. In this case, the parent 1 level education. So this I just copy and paste from the dictionary itself what those column means. So because you're gonna see in the category column, you're just gonna find integers, so you wanna trace back those integers to actually groups of people. So we have less than 7th grade, junior and high, to level of education in general. So what I did is that I plotted a count plot, simple count plot, and then we can see ADHD outcome, yes or no, and all the variables. So by looking at it, you can like be tricked into kind of like, you want to visualize, of course, as I said, you want to identify potential patterns and trends, and you want to like you want to see if there's any class imbalance and inform how to handle such. But you want to just know, if I include parent 1 education as a predictor, is it gonna give me more information? Is it actually predictive of ADHD? So that's what we're trying to kind of like understand while performing ADA, in this case for this data visualization. So first of all, you kind of like, from the observation, most of the data, you can see that most of the data falls into the specific category, 21 category. So and most of the ADHD data falls in that category. So you might be tricked in thinking that like, oh, so most of the people that are who have a parent whose parent 1 education is, I think, graduate degree, are gonna have ADHD. So actually education is predictive of ADHD. Well, that's not entirely true, because if you go back, and you probably already knew, but I just want to make sure that that's clear. But if you go back into the value counts, most of the subjects in this data set fall into the 21 category, or the kind of like higher education category, the parent 1 higher education category. And so to address this cost imbalance, you wanna so this means that even if ADHD prevalence appears higher in these categories, it might just reflect that there are more people in this group overall rather than an actual trend. So to address this, we want to normalize the data. We actually don't go over how to normalize the data. What I did is that compute percentage, because I think it's really easy way, straightforward to see it within each category to account for difference in group size. So you want to compute the ADHD percentage for each category. So I computed that, and you can see that the higher percentage is in the 3rd category, which I think is one of the lower education, so less than 7th grade. But before you want to, jump in any kind of like conclusion, also lower education is predictive of ADHD outcome and things like that, you want to notice back up here that this category actually has just 5 subjects. So there's really a big class imbalance, because the kind of like the higher education has 470 subjects, and the lower education has only 5. Of course, like, while this proportion might appear noteworthy, it is essential to, like, this proportion that I just saw, like this percentage, it is essential to consider a smaller sample size for lower education level. We just have 5 subjects, so smaller sample size can lead to greater variability, right? Of course, if you're gonna have 4 out of the 5, you're gonna have 80%, right? And that was gonna make the proportion more susceptible to, having a smaller data size that makes the proportion more susceptible to outliers. And this means that also a few individuals' cases can disproportionately affect the results, since we just have 5, right? Making them less reliable and less representative of the broader population, right? Because compared to higher education, we have almost 500 subjects, right? So there's really a big class imbalance. Therefore, it's crucial to examine sample size carefully before drawing any conclusion. That's, I think, the conclusion that we can take from the kind of like the that we can take from just looking at this class imbalance and looking at we have such a smaller sample size for this category, so we should not draw any conclusion in whether categories or whether parent one education actually leads to ADHD or not. We don't know because there's a really big class imbalance. So smaller sample size can lead to greater variability, so we cannot conclude anything. And I think now I'm gonna switch it over to Kylie.
Thank you, Caterina, for the exploratory data analysis. And now that we have explored the data a little bit, we can actually go into processing the data to be prepared for machine learning. Before we do that, I'm going to direct us to the data dictionary that gives us details on our categorical data, because our categorical data frame has been pre-processed beforehand. So this categorical columns includes, demographic data about adolescents, and then also like parental information such as occupation and education level. But as I said, this data set has been pre-processed by assigning numerical values to the categories within each variable. So if you see here, for instance, in the parent one occupation column, the number, 35 might represent roles such as nurse, skilled technician, medical technician, or a counselor, and there's even more in that category as well. This grouping reduces the number of unique responses for each variable, and it simplifies the data set. This makes our categorical columns all like int variables now, with those int representations all found in this data dictionary. And while this pre-processing is useful, we still need to apply something called one-hot encoding to optimize our machine learning model. And what does one-hot encoding do? One-hot encoding creates a new binary column for each unique category within a variable. So for example, in this parent one education column, we've got those 10 possible categories, 0, 5, 10, 15, 20, etc. And one-hot encoding will generate 10 new columns. So we're going to have a column named parent one education 0, parent one education 5, parent one education 10, and so on. Each of these columns will contain Boolean values, true or false. For instance, if the participant's parent one occupation falls into category 0, the parent one occupation 0 column will have a value of true, and the rest of those 10 columns will have a variable of false. And the same logic applies to all other categories, ensuring each participant is appropriately represented in the dataset. And you might be wondering why we perform one-hot encoding before machine learning, especially since these, categorical columns are already pre-processed and they're integer values. And many of you may know that, they could be put into a machine learning model since they're integer values now. But if you were to use these integer values, our machine learning model might interpret these numbers as having some like meaningful order or scale. So you know how it's like 0, 5, 10, since that's like gradient up, it's going to think that that is like has a meaningful value, and it's going to lead to some incorrect assumptions. So one-hot encoding avoids implying these ordinal relationships. And it eliminates this problem by assigning each category its own binary column, ensuring no ordinal relationship is applied. And in general, one-hot encoding also just improves a lot of machine learning algorithms. A lot of popular machine learning algorithms perform better with one-hot encoded data because it provides those clear distinctions between categories. And without one-hot encoding, algorithms might struggle to learn from categorical variables or produce biased results. So now that we understand one-hot encoding and what it is and why we do it, let's switch back to Jupyter Notebook to see how we actually execute this code. So if we want to scroll down a little bit to the coding part, one-hot encoding is only possible on categorical variables. So since we have pre-processed these variables to turn into ints, representations, we are going to actually have to turn them into categorical variables, or like category D types, before we do any one-hot encoding. So we use that simple for loop that you can see to turn all int variables into categorical variables instead. And another step we have to take before using one-hot encoding is that we have to notice that our first column of all of our data sets is this variable called participant ID. And this is the indicator variable that identifies each patient. This column is very important as it will be the one used to merge all of our data frames together. But we do not want to encode this column. All of these, so participant ID has a unique value for every one of the 1100 rows that we have. So if we encoded this participant ID, we would have 1100 new columns of binary values, and obviously that is not efficient. So I'm going to create a list of all the columns except the first one. That's what this code is doing. That's the columns to encode variable is a list of all the columns except the first one in our categorical data frame. And then we will use the pandas get dummies function to execute one-hot encoding. And we can do this only on our columns to exclude list of columns. Columns to encode. And that's going to only encode the values, all the other columns other than participant ID. And as I mentioned a little bit before, but this get dummies function is going to execute one-hot encoding, and it will convert selected categorical columns in our train categorical data frame into one-hot encoded columns, creating binary true or false columns for each category. After we use get dummies, we're going to use apply map. This function converts those true and false binary values to 1 and 0, 1 for true, 0 for false. That's just to make these variables ints and ready for machine learning because we don't want true or false values. And after encoding our categorical columns, we will add back in the participant ID. The get dummies function will align the participants correctly with their respective feature variables because it respects the original index of the data frame. So row alignment is consistent if you are worried about that. So when we concatenate our data encoded with the rest of the data frame, here it's the train cat.drop columns equals columns to encode. So that's the participant ID column. When we concat that with our data, our encoded data, the rows will align because pandas automatically matches that index. And then as you can see, we'll have a fully encoded categorical data frame. So we have done that for our training data set, but for any machine learning model, you need training and test data. On our Kaggle data page, you'll find both the training and testing data frames, and you will need to, download all of those. And we have just encoded the categorical data frame for our training data, but we need to apply the same encoding steps to the categorical data frame in the testing data. It's essential to ensure that any preprocessing done on the training data is also applied to the test data to ensure accurate model predictions. Our test categorical data frame is preprocessed the same way as our training data with those, the numerical values assigned to the categories. So we will follow the same steps to encode the data frame. So I put the code for the test data as well, but we will just, convert those integers to categories, select the columns that we want to encode, use get dummies, and apply a map to execute one-hot encoding and combine back with participant ID column, just as we did with the training data. Now we have categorical data frames for both our training and test data sets that are both ready to be merged with our remaining variables. These include the functional connectome matrices and the quantitative data. After we do this merging, we will have two final data frames, or almost complete data frames, our train data frame and our test data frame. And like I mentioned before, all of these data frames include participant ID variable. This serves as the unique identifier for each patient. This variable will be used to merge the data frames as it is the only common variable across the data sets. We're going to use pandas merge function to merge all of our data frames, but it only allows us to merge two data frames together. So I will first merge our encoded train categorical data frame with our training functional connectome matrices. Make sure you know that they're all the training data frames. And then I will combine that merged data frame with our training quantitative data frame. Again, this will all be executed using the pandas merge function on our participant ID variable. And now we have created an almost complete trained data frame. You may have noticed that there is one data frame that we have loaded into this Jupyter notebook that we have not used to merge yet, and that is our solutions. When training a machine learning model, though, you have an X-trained data frame containing the feature variables and a Y-trained data frame containing the target variables. We have just created our X-trained data frame containing all of the feature variables needed for our machine learning model. And in our third workshop, we will cover how to use this X-trained data frame that we just created and our Y-trained data frame, which is our solutions, to train the model. Our testing data, though, does not contain any solutions, if you notice that on the Kaggle page, as that is what you will produce when running your model. So all we will do is create that feature variable data frame, and you will run that through your trained machine learning model, and then you will output, the solutions. That's the point of the challenge. So now we have to create that feature variable data frame for our test data, and we will merge together the feature variables for our testing data the same way we did for our training data. First, we are going to use the pandas merge function with our encoded categorical data with the functional connectome matrices for our testing data, and then we will merge that data frame with the testing data for our quantitative data. And then we have created our final feature variable data frame for our testing data. So we have just created our X-train feature variables for our training data and our feature variables for our testing data. These are almost complete data frames ready for machine learning, but there's one last step we are prepared that we need to do before machine learning, which is imputing our NA values. And I will pass it on to Leah to explain how we will demonstrate this. But one thing I want to note before that is that, again, just like we did with the encoding, you're going to have to pre-process it the same way. So whatever way you process the training data or impute the NA values in the training data, you're going to want to do to impute the values in the testing data as well for accurate machine learning models. But yeah, I will pass it on to Leah to explain more about NA values.
All right, so before setting up the data for machine learning, again, what Kylie mentioned, we must address the missing values or not a number of values to ensure optimal model performance. So first, what are NaN values or NA values? There are a lot of terms for it, but it basically means the missing data. And the problem of missing data may arise from issues regarding like data collection and curation, depends on how it was handled and such. So in this workshop, we will be demonstrating two very simple ways of handling missing values. And this is by getting the mean of each category or column and using the mean to replace the missing values. And we will be also working with backward fills, forward fills, etc. But again, there are multiple methods of handling null values. And so it is recommended that you experiment with different methods. And of course, the methods that you will be using to handle these missing values or these outliers can also depend on, of course, how your data looks like, how each variables interact with each other. So it's really recommended that you go through the data dictionary, you do your exploratory data analysis before jumping and before figuring out what method to use. So some include substituting these null values with the mean, median, and mode of the column. You can also try dropping the rows with null values, or lastly, replacing these with a constant and arbitrary value. So for this workshop, we'll go ahead and jump to our notebook. We will be demonstrating substituting with the mean and also using different fills, or like the nearest neighbor fill. First, I think it's important that we load the train DF dataset. As you can see, we have 371 null values in total. And then if we go ahead and fill these null values or input these NA values with the mean of these specific columns with different missing values, then you can see that the output itself, or the sum of the NA values, is equal to 0. And then we can also use backward and forward fills. Specifically for this data set, we tried both backward and forward fills. Backward fill was not capable of making all of the missing values into 0, so there were still leftover missing values after the backward fill. But as you can see in this code, we used forward fill, and it did lead to a sum of 0 for our missing values. And so again, what Kylie mentioned, it is important to remember that this process of removing null values must be done for both data frames. So you have to repeat this process of removing missing values for both the testing and the training data frames. So now this prepares the data frame, and it allows it to go training for machine learning. And machine learning is specifically machine learning and the details of it and how it's going to work in this datathon. This will be the main topic actually for our third and last workshop on February 5, 2025. So this workshop will be on how to build your multi-outcome machine learning model. We're going to talk more about our accuracy score and also explaining F1 score as the metric for our model evaluation. So this will be our last workshop. So we hope that we'll see you there as well. Yeah, so again, thank you so much for attending our workshop. We'll now be opening the floor for any questions that you have for us.
Awesome. Thank you so much to our presenters. We do have some time for Q&A. And so here's a reminder to our audience to put any of your questions you might have for our presenters in the chat. Here are a few questions that have already been answered, but I want to just make sure we touch on this. The notebook from today's workshop will be posted right after this presentation, so keep an eye out for that. If you have any questions about the actual data sets, Valerie posted a link in the chat, so please refer to the resources posted there. Again, for any questions about the data sets themselves. Let's see. There was a question about if you can use Google Colab or VS Code for the Datathon, and you are absolutely welcome to use any tool that you like for the Datathon. And if you were not able to attend the first workshop where our presenters walked through the challenge goals and the data sets, you can access the recording for workshop number 1 in the community hub and on Kaggle. All right. So let's see. There was a question on the chat about some of the histograms that we went over in the EDA section. Specifically, there were 2 plots that looked at the bar plots of the target variables ADHD and of sex. The question asks, we looked at these 2 target plots separately, but do you think we should look at the combinations of male and ADHD, male non-ADHD, and so on?
Yeah, that's great great way to look at it. I would definitely suggest look at it that way, because it can give you a lot of insights on because the whole thing is about also how ADHD impacts differently genders. So I think it's really important to combine those, because at the end of the day it's gonna be a multi-outcome model. So you want to see how also those 2 categories interact with each other. So yeah.
Okay, great. There was another question about the one-hot, or not one-hot encoding, the missing value imputation. The question asks, we go through this EDA process. Each category might have class imbalance or outliers, but before I see that, I need to convert to the right data type and drop the NA values. So would I do the visualizations of the relationships of the features and target variables when I go through each feature to convert the type? Or do I do the visualization all at once after I have converted the data type? So just a little bit more clarity on the order of the EDA and the process of dropping or determining what to do with the NaN values?
I think you could try to do some exploratory data analysis both before, imputing those NA values and then maybe after as well. But why we did it before everything else is because you don't want to do any EDA after you've already like encoded the categorical values or one-hot encoded the categorical values. But yeah, I think it's possible at any step in the process, especially if you have more questions as you continue to work through.
Yeah, and I think it's also like always a work in progress. Look at you can fit the model first and then go back and like modify some things, whether the encoding or like the how you handle missing values. So you can definitely always like try new different ways and try how your model performance always improves.
Absolutely. To their point, it's an iterative process, right? Looking at the data initially, looking to see, okay, do I have missing values in this respective column? What can I do about this? And then kind of going back and forth within the EDA process to make sure the missing values are handled properly. So great, thank you. I see we have about a minute left. I should note here that for any question that we don't get to live, we will post the answers to your questions on the hub so we can address your questions later. So don't worry if you don't get your question. Maybe the last question that I will ask will be about dimensionality reduction. This question asks, the fMRI dataset has about a little over 19,000 fields, more if we do one hot encoding. And the training data only has about 1,200 rows. So how would you suggest that we deal with that many fields for modeling? And are we going to really look into feature selection and feature reduction in the next notebook?
That's a good question. We can definitely, I think in the next workshop, we're definitely going to focus more on like what is a multi-outcome model, what is F1 score. But we can definitely add more onto like feature selections and how to do that because we went over ADA and ADA, the whole point of ADA is also like to select features that might be more predictive than others. And that can make your machine learning model stronger. So we can definitely, if that will be helpful, we can definitely go over some of it and just explain more, especially because we went already over ADA. So it's just gonna be the next step after ADA. It's to also like feature select. So yeah, definitely we can go over that.
Well, all right, that concludes today's workshop. Thank you again so much to our presenters and to everyone for joining today. We look forward to seeing you at the next workshop again on February 5th. Yeah, see you there. Thanks, everyone.
Thank you.
Thank you.
Thanks, everyone.